In this section, we're going to look at data redundancy. Specifically, we're looking at how data availability and data protection are implemented in the arrays. The first architectural choice here is a shared controller, shared shelf environment that is favored by both Extreme I/O and Pure. In this environment, individual disk redundancy is provided through a RAID array. And this RAID array and the parity striping that goes along with it is used to be able to protect against individual disk failures. RAID is a pretty straightforward construct and is pretty well known, and so the use of hot spares in order to be able to automate the rebuild of a RAID array without manual intervention, as well as the performance overhead that is required while that rebuild is happening, is pretty straightforward. In the case of a controller failure, the other controller will take all of the performance and all of the I/O, all of the bandwidth for the entire array, and that controller will have to be replaced before system redundancy is restored. In the case of a shelf failure, there will be data unavailability or data loss depending on what type of failure it is. Now, disk shelves don't have a whole lot of moving components, so the risk of a failure of an entire disk shelf is low, but it does end up being a single point of failure in this architecture. The other architectural design choice that can be made for system redundancy is a shared nothing environment. In this environment, which is pretty exclusively used for large scale-out implementations, there's no sharing of hardware between any of the nodes. Each node is its own controller, each node runs its own copy of the storage software, each node manages the disk that's in it. All of the nodes are interconnected through an Ethernet mesh that's in the background, and this mesh is what's used to be able to protect against both disk and node failure. In the case of a disk failure, all of the additional disks in all of the additional nodes in the cluster will be used to reprotect the data that was on the disk that was lost. This same model happens when there's a controller failure, where a mesh of all of the nodes that are remaining inside the cluster will be used to rebuild all of the data, to reprotect all of the data that was on the node that failed. This architecture is used pretty exclusively in large distributed storage systems, and in conjunction with the ability to scale and the ability to load balance across it, allows for good scaling and good performance while maintaining the integrity of each of the individual nodes. In summary, both shared disk and shared nothing provide the system redundancy that customers need out of their storage environments. In the shared disk model, the starting point for the number of controllers that need to be used is smaller, and so generally the initial outlay of capital in order to be able to deploy the cluster is smaller. But the total percentage overhead that is required to maintain that system redundancy is high. In a dual controller array, 50% of the controller resources that have been paid for and implemented have to be used in order to maintain redundancy. In order to repair any failure that was made, hardware replacements have to be put in place, whether that's at the controller level, whether that's at an individual disk level, or whether that's at a shelf level. In a shared nothing environment, the initial scale is larger, meaning that 4 nodes are required in order to be able to establish a cluster and establish system redundancy. But as the environment scales, the total amount of resources that are required in order to maintain that redundancy come down as the number of nodes in the cluster increases. This works best in environments that are going to be distributed, environments that are going to scale quickly and unexpectedly, and environments where being able to balance the amount of performance versus the amount of capacity required is a necessary part of the operational process of the array.